I'm just going to start now. Good morning, good afternoon, and good evening to all of you who have come today for this last session of the spring semester IAS seminar series. Today, we are very happy to introduce Carter T. Butts, who will be speaking on the statistical mechanics of social networks. My name is Hendrik Ertz, and I'm a PhD student here at IAS. I will be chairing the session and moderate the discussion after the presentation. But first, let me introduce today's speaker. Carter T. Butts is currently a professor of sociology at the University of California, Irvine, and also affiliated faculty of the Department of Electrical Engineering and Computer Science. His main research interests are, among others, mathematical sociology, social networks, as well as judgment and decision-making. Most recently, he was able to secure a grant on COVID-19 risk communication on social media. Before coming to UCI, Butts received his undergraduate degree at Duke University in systems theory and subsequently graduated in sociology from Carnegie Mellon University. His dissertation on spatial models of large-scale interpersonal networks received the Herbert A. Simon Doctoral Dissertation Award in 2002. He has contributed to many network-related streams of research and strives to combine mathematical models with network data at hand. He has a very clear language and provides strong arguments for statistical mechanisms which allow to explain certain properties of real-world networks. Finally, aside from the theoretical research and advancements of network science, he is also a very productive developer of software packages, more specifically packages for conducting such network analysis using the R programming language. Among his many awards and honors are the James Coleman Paper Award by the ASA section on Rationality in Society, the Leo A. Goodman Award by the ASA section on Methodology, and the William D. Riches Software Award. Let me close with a few announcements and formalities before I finally hand over to Carter. I've just mentioned that this is the last session of this seminar series. However, this certainly isn't the last public lecture IAS organizes. The next will commence in September. On Twitter, IAS regularly announces these lectures, new publications, and leading research in the realm of analytical sociology. So in order not to miss anything, I warmly invite you to follow the official IAS Twitter account using the handle IAS_LIU. I will be sharing this in the chat as well, so you just have to click a link. Also, while today's lecture is a last, I'm more than happy to announce a first. On Monday, Alex Gimenez de la Prada will defend his dissertation thesis publicly. He's the first PhD student graduating from the Institute for Analytical Sociology, and as such, it is a big day for the whole institute. Therefore, we would like to extend an invitation to all of you for attending the public part of the defense. The event will commence on Monday at 1:15 p.m. Stockholm time, and anyone can attend via Zoom. If you are interested, I will be sharing the details for that in the chat as well. Lastly, please note that this lecture is going to be recorded. Note that this only includes the lecture. We will not record the following discussion. You can find many recordings of the presentations held on our YouTube channel, to which I will share a link in the chat momentarily. Also, I would like to invite you to also subscribe to the channel to be among the first to be notified whenever a new recording is made available there now and in the future. But now, let us transition to the reason we are all here, progress in the statistical mechanics of social networks, presented by Carter T. Butts. Carter, thank you for joining the IAS seminars, and the floor is yours.
All right, well, thank you so much. Well, first of all, thank you for the invitation. It's great to be part of this series, and I want to thank all of you for tuning in today. As the talk indicates, today I'm going to be talking about work that my group has done and my collaborators have done, but also some other things going on in the field involving the statistical mechanics of social networks, and we'll get clear about what that is as we go forward. But as some background for what I'm going to be talking about, I sure first wanted to note that, as many of you are well aware, the last couple of decades have seen enormous progress in our ability to model networks, and particularly using stochastic process models, that is random graph models, if you like. A lot of that work has really focused on the statistical side of things. So trying to develop well-grounded inferential tools so that we can test hypotheses, we can estimate parameters about the kinds of factors that might drive network formation and change, computational tools for simulating networks, and so forth. What has been a little slower to develop, but is starting to emerge, though, is a body of theory that links cross-sectional network models to social mechanisms. And this is the statistical mechanical part of things, where we have a model, if you like, a sort of macro model for the structure of a graph as a whole, And we want to learn things from that about the underlying microprocess that might have generated it, even when we can't see those processes directly. So today, what I'm going to do is I'm going to talk about a few examples of recent work that I think supply substantive insights that are emerging from the new generation of network models. And we'll see how we can connect the models that might be, on the one hand, seen as kind of just quote unquote just statistical, as just trying to fit data. We can get real insights out of them about an unobserved process. But also I want to illustrate how we can make connections between ideas from the social sciences about social networks and ideas from statistical mechanics coming out of the physical sciences to inform network analysis and of course, proximately analysis of social networks. But time permitting, I'll also show an example where we've done the reverse and we've taken ideas from social networks and actually applied them to physical problems as well to solve things that have been very difficult to address in that arena. So to begin all of this, I'm going to start with a concrete problem, and that is actually an old problem, not a new one, a sort of classic. And the problem is, why don't I have more friends? Well, you may not think of that as really a classic problem. Maybe it's a personal problem. And you may have some theories about why I don't have so many friends, but hear me out. I want to argue that this is something that goes beyond me personally. And the problem begins with an observation, and that observation is that if we go back over the last few thousand years, human populations have grown enormously. So if we go back to ancient times, we find that world populations grown by a factor of at least 10 to the third. So our networks, at least the network of all humanity, has grown enormously since that time. But some things haven't changed very much. And in particular, the mean degree, that is the average number of ties we have, has not changed much in most networks. So if we look, for instance, at kind of loose interactions like acquaintanceships, estimates based on band interactions in early human societies estimate that people used to have about on the order of 10 to the 2 contacts, so about hundreds of contacts in those societies. Modern numbers, if we do acquaintanceship studies, they still are 10 to the 2, 10 to the 3, so hundreds, thousands of contacts. So they have not gone up by orders of magnitude, even though the populations we're in have expanded. Likewise, I don't know about you, but most people I know don't have thousands of sex partners, tens of thousands of friends, and so forth. And although no one was doing social network surveys in ancient times, we can go back and read literature, look at descriptions of life in ancient China, in Japan, in Greece and Rome and other societies. And what we observed is that the lives of those people were very much like the lives of people today. We have see no evidence that the number of personal ties people had in their interactions were substantially different from what we see today. So this is kind of a puzzle, okay? On the one hand, networks are larger than ever, but the average number of ties we have is not. And that's a general phenomenon. This is a phenomenon that goes by the name of mean degree and variance. And it's something we see in many, many kinds of social networks. That when we compare networks of different sizes, what we find is that as size changes, the average numbers of ties people have tend not to. So here are just 3 examples I plucked out, just illustrating different cases. The top right are radio communications in the World Trade Center disaster, so an emergency setting at the individual level. The bottom right, collaboration in the Hurricane Katrina response, so that's an organizational level setting. And then the bottom left was friendship within schools, so a much more conventional setting. And in all of these cases, if we plot the size of the network, n, against the density, we see the density declines as about 1 over n. And the mean degree, the average number of ties per node, stays about constant. It doesn't change a whole lot, even though the networks may vary by orders of magnitude in size. And so this is something that we see over and over again in social networks. And yet it can be puzzling. Now, why would it be puzzling? Why would we expect them to change? And to understand that, we need to go back to how we think about where networks come from. And especially when we model networks, the kind of hidden assumptions about the processes that give rise to them that are behind those models. And so to begin with that, I want to go back to sort of the earliest days of people thinking about how to model networks and the kind of simple models that they began thinking about. And so the very typical paradigm that goes back to the early days of network modeling is to think about a fixed set of individuals, say a group, like say a classroom, like we might envision something like what's illustrated by the case on the right, which is, by the way, a beautiful network visualization from the days before computers. So this was actually done by pasting little pictures onto to paper here back in the 1950s. But we might imagine we have, say, a classroom setting, and we have, say, a liking or a friendship relation, and we imagine each student is asked to nominate people that they like or that they're friends with. And a very simple model we might imagine is that each person nominates the others with some probability. And if we were thinking about a baseline model or a sort of starting point or null model, we might envision a model where each child nominates the others at random. So there's a certain probability for any given individual that I'm going to say you're my friend, right? And I just go around and nominate people randomly. And this idea is very old. Actually, it goes back at least to Moreno and Jennings' work in the 1930s. So anytime people tell you that, networks is a new field, okay, it's not. People, in fact, have been having random graph models since the 30s. They didn't have computers back then, so they simulated them by drawing things out of an urn. It was quite a profound achievement given the technology. But so this idea is very simple, and it's a very natural idea, right? If we're thinking about how to model things, starting with the idea that, okay, we're going to have everyone looking at everyone else, and with a certain probability, I just nominate each person, is a very natural starting point. And that starting point still is with us today, hidden within the network models that we use. So here's a newer way of thinking about network models. This is a particular way of writing down network models that are called ERGMs, or exponential family random graph models. Some of you may be familiar with them, some of you may be less so, but I will be using this idea a lot today, so I'll lay this out. And so the way an ERGM works is summarized by this equation that you see here in the middle of the slide. So the idea is that I have a random graph, I'm represented by capital Y, on some finite support represented by script Y. That's the set of all the graphs that are possible. And we can write down the PMF of that under some very weak conditions in the following form. And so this equation says, in essence, that we have a series of features that are represented by this small t. And these are properties of the network, possibly with covariates. We have a set of weights on those features. And we can make a score out of these by multiplying the weights by the features, right? So we can, so we have graphs that have lots of the features that have positive weights at a higher score. If they have less of the features that have positive weights, you get a negative score, and the reverse for negative weights. And we assign more probability to graphs with a higher score by just exponentiating that weight to make it non-negative and normalizing it by summing by the same thing over all of the support. And then we also have this term H that floats around called a reference measure, which is just a function of the graph and nothing else. And so that reference measure looks like a sort of a nuisance. And indeed, if you look at a lot of papers in the area, you won't see the reference measure. It won't show up in the math. And that's because often this is just taken to be an indicator of whether or not the network is in the set of the support. That is a possible network. And we give it a 1 if it's in the network, if it's in the set, that is possible, and a 0 if it's not. That's called the counting measure on the support. And to understand what that does, we can think about it by saying, well, what if we were to make all the parameters in the model 0? That's like we're going to turn off all of the different biases and things that shape how the network works, the influence of the features and the covariates of network structure. And if we took all that away and we made those things 0, then that e to the theta transpose t would just become 1, and we would just be left with the ratio of the h's. Well, and if the h is just a constant, then that's going to tell us that the probability of seeing any given graph is just going to be 1 over the number of possible graphs. And that's just saying that when all the effects are turned off in the model, we just have a random graph, right? And that's exactly the original model. That's our guessing model. So all these fancy models we write down today with all these fancy terms in them have underneath them the idea that we start with a world where people are just kind of forming ties at random with other people, and then all the other terms of the model are going to start with that baseline and then modify it to make some kinds of ties more likely than others, or to create dependence between different ties, whether if one tie is present, it might affect another. But under the hood, we begin with this idea of people just nominating each other at random. And so we can build complicated models on this. If I didn't show you a real one, they revoke my credentials. So I have to show one. So this is my mandatory model. It's the most complicated model I'll show you today. But this is just for the people who haven't seen it, to fix ideas. So this is an example of a model fit to some classic data by David Krakart. These are managers in a high-tech firm. These are nodes. The ties are reciprocated personal friendships, so people agree that they're mutual friends. And we can fit a model, the type I just described, the data. We have the statistics in the model are the terms that represent the different forces that shape the network. So there's a term that counts how many edges there are that has to do with the overall propensity of ties to form. We can have a term for reciprocity, or sorry, not reciprocity, but for homophily. That's called node match in this case, and that has to do with whether, in this case, people in the same department are likely to choose each other, and the answer is yes. And we can look at things like triadic closure. So there's a term here called GWESP that has to do with the propensity to close triads, and that's also present. We can test hypotheses. We can estimate the strength of effects. We can even simulate. So we can fit the model, we can simulate it and see, does it recover other properties of the graph, which it does here, the degree distribution, the shared part distributions, and there's lots of stuff we can do with that. And there's an entire field that focuses on how do we do this? How do we do it with large networks? How do we do it with complex networks? And it's becoming an increasingly mature area. And so we're getting very good at doing that. And that's led to a lot of great innovations. But what I want to focus on today is not that, and not the complexities of it, and certainly not the inferential side. What I want to do is go back to that early part, that baseline part, and talk about the foundation on which all the other stuff is built. And I'm going to talk about that vis-a-vis something I'm going to call the reference model. Now, the reference model sounds like the reference measure, right? And in fact, the reference model is the reference measure plus all the other terms that we would sort of always in our given setting put into the model. So for instance, when we model most social networks, we always include an edge term, right? It acts like an intercept in a regression. That's that average level of interaction. And then all the other stuff might or might not be there. Those are things that we have to, that represent other kinds of forces that might shape the network that we want to understand. And so if we want to think about, well, what's going on in the network before we include all these other things, we can take our model that we wrote before. So this is just the ergon we had before, and I'm going to split it up into two parts. There's the part in red that's our optional part that has all the other cool stuff in it that we're interested in. And then the boring part in blue, which is the reference measure, plus like your intercept-like effects that you always put in there. And so if we now say, well, what happens if we take out now all the fun stuff, all the red stuff, we're just left with the part in blue, and that's the reference model. So this represents basically where you start before you put all the complexities into your network. And I want to think about that model because it turns out that model has some important implications for how social networks work. And so in the standard case, the typical models that we usually fit on a day-to-day basis, typical things people assume are the counting measure, and that's just that they take the reference measure to be constant, and they put the edge count in, which again is controlling for density. And so if you ask, well, what's the reference model that you're using implicitly when you do that, whether you're thinking about it or not, the reference model that you're using is a homogeneous Bernoulli graph. And that's a fancy way of saying it's just a random guessing model where everyone has some probability of nominating someone on the tie, say nominating someone as a friend, and then it happens at random. And then all the other effects are modifying that baseline. So again, we're back to that intuition of our little group where everyone in the group just goes down the line and says, okay, you're going to be my friend, let's flip a coin, yes or no. Or you're going to be my friend, flip a coin, yes or no. And then all the other things shape whether or not the coin flips are linked to each other, whether some coins are more likely than others, and so forth. And that's that basic model under everything else that people usually use. Now, there's nothing wrong with that. That's a great model for a lot of settings. It's very natural, and it's been very productive. But it does lead to some problems, and those problems have to do with my missing friends. So let's get back to my missing friends. What's up with that? Okay, so the issue here is that in our Bernoulli reference model, right, this assumes that in baseline, before we add anything else to the model, the density of the network is fixed, or the expected density is fixed. We have a fixed probability we're going to nominate people. Now, it turns out that if you have a fixed density, a fixed expected probability of nominating people, then the average number of ties you have as the network grows has to grow as well. And in fact, it has to grow linearly. So when you get what's in this top right panel, right? If density is fixed, mean degrees got to go up linearly. That's just a function of networks. That's how they work. If you had Martians and they had networks, it would work that way for them too. The problem is the real world doesn't look like that. It looks more like the bottom panel, right? Where my average number of friends would stay constant if the network grew, right? I'm not going to suddenly get massively more friends, and that means the density has to fall. So models that have this type of baseline structure underneath the hood are going to be problematic. They're not going to generalize well. And moreover, the fact that that's not what happens in the real world also means that there's something missing in our thinking, that simple model is missing something important about how the world works. And the question is, okay, what do we need to do to modify that underlying reference in order to get realistic behavior? Well, so one idea is, well, okay, what if the thing that's fixing the issue is just that people can only have so many ties. You only have so many friends. Or you can pack people in like these stick people on the right, and at some point you've packed everybody in, they just can't interact with anybody else. And that's been posited before, right? That there's an upper limit on how many ties a node can have. If that were true, that would certainly fix our scaling problem, right? Because if my degree has to be less than some maximum d, then when the network gets big enough, eventually I'm maxed out, and that means that our density will have to fall as 1 over n, which is what we want. We can re-express that model in ergom terms as well. And in fact, we get a reference model. It looks a lot like we had before. The only difference is that we change the support from the set of all graphs with n nodes to all the graphs that have n nodes and where the maximum degree has an upper bound. And so that's one plausible model. People have talked about that idea at least since the 1970s. People like Mayhew talked about this. The problem with this model is that if you actually play it out, it leads to unrealistic things. And so since we can write this down in ergom form, we can simulate it, and we can actually see what happens when we have a model like that. So if we have a fixed baseline propensity to form ties, but we max people out and you're not allowed to have too many ties, what starts to happen is, on the one hand, mean degree does asymptote, which is sort of what we want, as shown in this simulation on the right. But the other thing that happens, as shown by the red line on the right, is that people start to saturate. So the way things are asymptoting is that more and more people are getting as many ties as they can possibly have, and they're not allowed to have any more. So you wind up in a world where no more friends for you until you finish the friends you have. You're not allowed to add even one more tie until you get rid of somebody. And there may be some networks like that, but that's just not typical of most human networks. In most cases, you're not unable to form new friends until you lose your existing friends. You're not unable to form new acquaintances until you lose your existing ones. In the real world, mean degree is just not saturated. And although there are some people who have advocated for this kind of view that this is the driver of things, this is just not very plausible for typical social networks. So that's not the explanation. And the question is, okay, what can we do? Well, here's another way we can think about approaching the problem. We go back to a random choice model. Another idea would be, well, what if we change the probability of choosing someone as a friend so that we made the chance of choosing someone as a friend in the baseline go down as the network gets bigger? So we're going to reduce the density by fiat. We're just going to say, well, my probability of choosing anyone is going to go down as the network size grows in order to keep the mean degree fixed. And if we do it, set it up just right, we can make all the accounts balance and the mean degree will stay constant. And we can do that. And in fact, in 2011, Pavel Krivitsky and colleagues published an important paper where they showed a nice way of doing this by changing the reference measure. They originally implemented it in a slightly different way, but this is what it amounts to. And so instead of having a reference measure that's just a constant that we can just ignore, they said, well, let's let the reference measure be n to the negative power of the number of edges. Or if you like, 1 over n to the power of the number of edges. And it turns out that fixes the problem, right? That actually fixes the expected density so that the mean degree stays constant. You can generalize this. So some work I did with Zach Almquist a number of years ago, we showed that you can then, with another very simple change, you can make the scale for arbitrary power laws in n. So you can, in fact, set things up where by just changing that reference measure, you can make the density change so that the mean degree stays constant or scales in whatever way you want. And so this, in some sense, wraps it all up. Okay, end of story. We fixed the problem. Yay us. So from a pragmatic standpoint, this was a great fix. From a theoretical standpoint, though, it raised some questions because it was just a hack, right? This is just saying we're just going to by fiat make this thing change, but it doesn't answer the question of why the mean degree stays constant. I mean, at least the maximum degree story gave you a reason to believe it, right? You have saturation. Well, here we don't know why the thing is modifying, and this creates some spooky questions. Like, if I have an edge variable, then in principle, according to this model, if that edge variable is in a big network, it should know that it should have a small probability of having a tie, whereas in a small network, it should know that it has a big probability of having a tie. Well, how does an edge variable know whether it's in a big network or a small network, right? How do I know that I should increase or decrease my nomination rate based on the network size, right? To have everything work out just so. And so this was sort of a disturbing question, and it suggested that, okay, maybe there's something else going on that's being missed. And so even though this is a great solution, mathematically it works, the question is, how do we obtain that from some kind of microprocess? Can we rationalize that in terms of some underlying scheme? Now, there's possibly many different microprocesses that might do it, so it's not necessarily only one, but what I'm going to talk about today is one approach to this problem, and it gives us a way of understanding where this mean degree scaling phenomenon might come from, at least in some kinds of networks. And so the idea is we observe that at the macro level, there is this relationship, it's there, We know how to model that at the macro level. The question is, can we find microprocesses that might explain it? And so the inspiration for how I'm going to think about this is the traces of things unseen, right? So if we think about a picture like, say, this time-lapse photo on the right, we see here this pedestrian standing by the side of the road. The pedestrian is not crossing the road. Why aren't they crossing the road? Well, they might have a lot of reasons for not crossing the road, but one of them is they get mowed down by all the cars that are passing. But we notice we can't see the cars, right? We can see in the time lapse just the trails of the cars. We can't see the cars themselves, but they're there. And indeed, the pedestrian knows that, and they're not going to get out on the road because they want to get run down. And this is a metaphor for a lot of things that we study in the social world, right? When we go out and we look at a social network, the network we observe is the result of many unobserved processes, right? People meet each other at Starbucks, they have conversations, they have arguments, they have all sorts of interactions, and all of these very short-term interactions wind up shaping the structure of the network. But these things operate on timescales that are much faster than the duration of ties themselves. And normally, when we see network, collect network data, we model network, we can't see these things. We usually don't have data on them, and we don't explicitly model them usually. But that doesn't mean they're not there, and it doesn't mean that they're not impacting the network. And so what this suggests is maybe this mean degree scaling is arising from the action of hidden degrees of freedom. That is, dynamics that are taking place under the surface that we're not seeing, but that are shaping the network as a whole. And so when we think about what kind of microprocess might do that, here's an example of one that can work. And so to build this, I went back to just very, very old ideas in network analysis. So the goal here, right, is to have a null process, to have a starting point, like our choice model. So the idea is we want something very, very basic. That's the beginning that all the things will modify. And so what's the most simple-minded thing we might imagine? Well, the inspiration for this is to say, well, let's go back to ideas like Peter Blau, Scott Feld, that made the point that in order to form ties with people, we often have to be in a common location. As Scott Feld puts it, we have to share a focus. So a focus is a context where people can interact with each other and potentially form ties. It might be a physical place where we might meet. It might be something like a Zoom session that we're interacting with. It might be an organizational context. But whatever it is, it's a setting where people can get together and form ties with each other. And so we're going to assume that behind our network, there are a bunch of foci, and I'm going to assume that there are M of these foci. We can't see them, but they are affecting the network. Now, the number of foci, reasonably enough, might well be related to how big the network is. And in particular, I'm going to focus today on the case where as the population gets larger, the number of foci is going to grow too. People will tend to spread out, if you like, in space or in social space in such a way as to maintain constant population density, right? So if things get too crowded, you form new areas to interact. If things aren't crowded enough and it's too sparse, you shrink how many places you go. Now we can change that and we can relax all of this. And that actually leads to really cool things. But for right now, we're going to work with this constant population density world. So we're going to let P be the average number of people per focus here. Now, people, of course, don't stay in one focus. So at any given moment, an individual vertex lives in a certain focus, but they transition. And in fact, they're going to transition all the time. Because this is a baseline model, we're going to assume that they transition at random in the baseline. And we're just going to let that be a constant rate Poisson process in continuous time. So at random moments, people get up and they move from one focus to another. Now, of course, they also, since it's a network model, they have to form ties. So we're going to assume a very simple model of tie formation, which is like our guessing model in continuous time. But we're going to assume that the formation of ties is limited to those within your focus. So at random times, those who are in the same focus who don't currently have a tie will form a tie with rate R of F. And then, of course, edges dissolve at random as well. Now, while you need to be in a focus with someone to form a tie, you can break up long distance. It's considered rude, but you can do it. It's been demonstrated. And so ties can break wherever the individuals are, and we assume that ties in the baseline are lost at a constant hazard rate of RL. And so that's going to be our model. We're going to call that the contact formation model, because when you're in contact is when you form ties. So to fix ideas, let's look at a little kind of cartoony illustration of how this works. So here we consider a world with 4 foci. We have a bunch of individuals that are in the foci. And again, at random times, an individual may decide, hey, wait a minute, maybe I'm going to consider moving. And they could move to any focus, including kind of moving back to the focus they're in. Let's say in this case, they move over here. Once the individuals are in the foci, they can form ties. And then when they move, of course, they drag their ties with them to new location. In that new location, right, they may then form new ties, which become part of the network as well. And then, of course, ties are also failing all the time. So again, whether you're in the focus or outside of the focus, ties may break, and this process iterates. And so this is our version of that kind of random nomination model, a very simple baseline model that lies underneath the rest. And the question is, can that baseline model actually regenerate this scaling effect that we see? And so to understand what that model does, we need to consider the interaction rates, because of course the behavior of that model depends on how fast things are happening. In particular, they're really heavily affected by the migration rate, RM, how fast do people move between these foci. And there are kind of two basic regimes that we might consider, at least two. One is a slow mixing regime. So what if I move very seldom relative to the tie turnover rates? Well, in that case, it's kind of a boring world where the vertices are kind of frozen in place. The network devolves back into a set of disconnected subnets, and it doesn't really help us. But what we're going to be interested in is the reverse. What happens when the migration rate is very, very fast compared to the tie turnover rate? So, you go, your ties may evolve on the order of months or years. If you're talking about friendships, say in adults, but, you go from place to place, you go to Starbucks, you go have meetings with people, you go take trips, you go have dinner with friends. These settings you're mixing in all the time. So in that case, your position with respect to the foci is completely blurred out, like in this time lapse relative to the network as a whole. But even when those positions are blurred out, they can still affect the network, as it turns out. And to figure that out, we can start by deriving the mean degree under these conditions. So we can characterize the system by the number of nodes, d bar, which is the average degree, and p here, which is that population average per focus. And with that model, because at random times we observe the model, the population within foci is multinomially distributed. In the large migration rate limit, we can work out the expected number of dyads at risk for tie formation. It winds up being this amount at the top. And then once we know how many dyads are at risk for tie formation, we can then obtain the mean degree by just solving for the equilibrium condition. So in equilibrium, right, we have to create ties at the same rate as we lose them, or otherwise we're not in equilibrium, are we? And so if we say, let's solve for the case where the number of ties created equals on average number of ties lost. If we do the math, we get this expression here at the bottom for d bar. And the important thing about that expression is that if we let n become large, that expression just reduces to a factor that is essentially the average number of ties that are produced versus the number of ties that are lost. And notice that it does not contain n. So the important thing about this is that it says, okay, our mean degree is going to be a function of the formation and loss rates and how big the foci are, but it no longer depends on the population size. So indeed, we have succeeded now in getting rid of population size scaling. This says in a big population, your mean degree should asymptote and it should not be affected anymore, which is what we knew that we needed to get to from a substantive standpoint. Now, the other thing in that reference model that matters is that the ties be independent in that initial reference. And so the question is, in that fast mixing regime, are the ties dependent on each other or not? Otherwise, it's not a Bernoulli graph, they're dependent. And it turns out that they do become independent. Proving that is complicated, so I'm not going to go through that today, but it turns out it's actually true. And the implication of that is that that contact formation model will regenerate that Krivitsky reference model or sparse graph reference model in the fast mixing regime. And in fact, not only does it recapitulate that empirical hack, if you like, it also gives us some insight into it because it tells us, for instance, why it might arise. And it also gives us an interpretation for the parameters of the model. So the parameter on the edge value in that model represents the baseline, the log of the baseline mean degree. We can now see that that's actually related to the formation rate and loss rate of ties. And that allows us to do other things if we wanted to generalize it and say, what would happen if we change the formation loss rates? Even though we can't observe them, we could actually speculate about what would occur, and we have a quantitative way to do that. So that's pretty cool. I will notice in passing that, of course, the slow mixing limit could be studied as well. I'm not going to say much about that other than to note that it's more complicated and it's definitely different and it does other things. So that's the thing I haven't worked much on, but for people who might be interested in that, that's another thing that one can do with this. So this even very simple process actually has other dimensions that are neat as well. But for our purpose, if we consider this fast regime, it does exactly what we need it to do. Now, that raises some other questions. So one question we might naturally ask is, okay, this is great, but it assumes that migration is really fast. And in the real world, how fast does it have to be for this to work, right? And so, it turns out that if we do simulations, we can look at this. So here I'm showing the migration rate relative to the formation loss rates. So 1.0 means it's the same scale as that rate. And then if it's higher than 1, that means it's faster. If it's lower than 1, it's smaller. So it's a log scale on the x-axis. The y-axis, I have d bar, the mean degree. And then in different colors, I show what happens if you change the focus size. So how many people per focus. What we can see is we see a characteristic transition from the slow to fast regime. The top dotted line is the theoretical d bar for the fast regime. And we do see that indeed this transition is independent of focus size. So that's reassuring. So it doesn't matter how big the foci are, which is good because we don't know that. You're going to get the same behavior. And then if we say how fast do things have to be, before we had the intuition that it didn't need to be that fast. And indeed, that turns out to be true. So about 1 or 2 orders of magnitude is adequate for time scale separation. So that is if the mixing time or the mixing time across foci is about 1 to 2 orders of magnitude faster than the rate at which we form or lose ties, then this will behave like that fast mixing model. And so now, is that fast enough? Can we do that? Is that achievable? To really know that, we would need some stopwatches. And here I have to complain about the state of the field. You know, the social sciences are good at a lot of things, but one thing they're not really good at is keeping track of time. There is no standard reference that I know of for the rates or durations of social processes, which is kind of interesting because in other fields, actually, some people have, you can find rates of how often, say, biological events happen or physical events happen, you know, how fast is protein expression, how fast is something diffused through a cell. Well, there's no equivalent reference for social processes. So those of you who are students, you want something to do, go out there with a stopwatch and start measuring things. But on an ad hoc basis, we can at least assess plausibility. So if we think about something like, say, student friendships that we know tend to turn over on the order of 6 to 18 months, how fast would movement in foci have to be to qualify? Well, anything that you shift in and out of on a matter of days is fast enough for this to work. So Starbucks is plenty good. Adult friendships that have a turnover of like 5 to 10 years, anything that you turn over on a monthly basis or so is fast enough, that's fine. In general, to turn it around the other way, if you think about sort of short term foci you're in and out of, intermittently occupied places like meeting spaces, classrooms, workplaces, if you have a 60-minute dwell time, that allows that's fast enough for anything where the tie turnover rate is greater than about a month. So this is actually very reasonable for a lot of kinds of ties. So this isn't necessarily the explanation for all things, to be sure, but it is something that's plausible for many kinds of ties that we might encounter. So this gives us some insight into that scaling and where it may come from. I also want to point out another interesting insight that we can get from this sort of modeling approach. And to get that, we're going to make a connection between the ergoms, which, you know, again, were originally created as statistical models. That is, models that were designed for inference from data, right? And of course, as we've shown, right, this has all these properties that we know and love. It has all these parts that we know and love, the sufficient statistics, the reference measure, things that we've talked about today. But this same kind of model can also be rewritten in a different way, because it turns out mathematically, this modeling framework is exactly equivalent to models that are used in statistical mechanics, right, which is a way of studying systems that was invented to deal with cases where you observe kind of macroscopic properties of the system that are produced by underlying microdynamics, but you can't see the microdynamics. So the statistical and statistical mechanics isn't about statistics per se, although they are related, as E.T. Jaynes famously showed, but it's about the idea that you're only able to deal with these sort of macro level things and you can't see the micro detail. And in a statistical mechanical model, you'd see something that might be written like this. And so some of you who've had some physics might recognize it. Some of you may not. And they're like, what is this stuff? What does it mean? But it has all these parts that turn out to map directly onto the modeling framework that we've seen before. So in a statistical mechanical model, instead of the reference measure, you'd have a multiplicity that represents how many ways you can get a particular, in this case, graph. Instead of having our linear predictor, so that's the theta transpose t, you have this thing inside the exponent that is the Hamiltonian, which is the energy of the graph, divided by -1/kt, where k is Boltzmann's constant, t is the temperature. So you have a scaled the scaled energy of the graph. And then instead of having a normalizing factor, you have something called partition function. But all these things are exactly equivalent to each other mathematically. So we can rewrite our model exactly in the language of stat and mech and vice versa. We can go back and forth. And this can be helpful because looking at things through the statistical mechanical lens can sometimes give us new ways to think about the features that we encounter in our other models. So for instance, if we look at the model we were just studying, notice that all of the things that we talked about, many of the things we talked about, involve changing the reference measure. So what we discovered is to get realistic mean degree scaling in a social network, we needed to change the reference measure from that constant measure that ultimately turned out to be about people nominating each other at a fixed rate to this Krivitsky reference, which we rationalized in terms of this underlying process of microdynamics where you can only nominate people when you're in one place. And what we can see here, if we look at that from a physical standpoint, that change is a change that's equivalent to change in the multiplicity. And in particular, changing that represents a change in the entropy of the system. And so in particular, the microstate entropy is up to a constant is going to be equal to the log of H, the log of our reference measure. And so we can think about this as saying, in essence, how many ways could this graph arise? How many ways could we get a particular network? Now, in the conventional view, in the view where we have the counting measure, this is proportional to 1, so the entropy is 0. This is equivalent to saying there's only one pattern of choices that would produce that graph. Every graph is a unique snowflake, unique microstate, and there's one way to get it. And this is our naive choice model. Now in the Krivitsky reference, that says, well, that's not actually where the graphs are coming from. There were these, even though the graph looks like it's a single thing, there are actually many ways to get that graph that we didn't observe. And so different graphs actually have different entropies because there's different numbers of trajectories that might give rise to one graph or another. And there's sort of a rough intuition for seeing why that would be true. Is if we think about it, in order to make an edge in that contact formation process, we have to co-locate vertices, and that places constraints on where the vertices can be, right? So there are fewer ways to put those vertices in slots if I have to have the ones that are tied be next to each other, right? And so the upshot is that there are fewer trajectories under that model that can produce dense graphs versus sparse graphs, and that becomes more and more true as the graph gets bigger and bigger and bigger, and there are more and more foci. And so the apparent microstates are no longer really the true microstates, if you like, and the entropy is not constant anymore. And so what that tells us is this is an opportunity effect, right? This is something, and that distinction is something that Blau and others, of course, in sociology famously have made, right? There are things that structure networks that have to do with choices, they have to do with our preferences, they have to do with social norms, social mechanisms, and there's some things that have to do with opportunities. They have to do with, do we encounter people or not? And so this is actually an effect of opportunity rather than the social forces themselves. And this is something that becomes more evident when we write it down in this other kind of language. Looking at things through this other lens can have other effects as well. And it can give us new tools for getting insights into things that we encounter with social networks. So here's an example motivated by something that one of my colleagues ran across a couple of years ago. This is Pavel Krivitsky. He was working with a network model that was a baseline model for sexual contact networks. And so this is a simple part of what would normally be a larger, more complex model, which only has two effects in it. It has a propensity to have ties, and it has a concurrency penalty. So this is a penalty for having more than one sex partner. And so this is a very simple piece of a larger model. And while he was working on code and trying to get some other things to work properly, he noticed this weird effect, which is that if you simulate outcomes from this model, you get this weird thing where you start out with people are not having much sex, there's not a lot of contacts, and then all of a sudden, overnight, bam, there's this transition where people are having a lot more fun, and suddenly there's a ton more sex contacts than there were before. Now, everyone's not having sex with everyone else, it's not a giant clique, and that is actually important for what I'm talking about later, but the rate is much higher, and the key thing is that this transition is extremely sudden. And so this was very surprising. No one had seen this type of thing in this kind of model before. Now, phase transitions have been seen before in ergoms, and in fact, they're quite well studied. The most famous kind, the kind most people know about, are density explosions, and they famously happen in models like the edge triangle model. So if I have a network with a propensity to form edges and then a propensity to form triangles, then it's been known since the 1980s, and the famous work of David Strauss, that if you have even the tiniest propensity to form triangles, then if the network gets big enough, you get a sudden transition from a world where you have very few triangles, looks like a random graph, to a world where like everybody's tied to everyone else. So if you like, you go from a world of anomie to a world that's a world clique, okay, where everybody's tied to everyone else. And although that makes for a great album, that's not so physically realistic. For the most part, we don't live in a giant world clique. And indeed, a lot of papers have been written about this phase transition, and there's been a lot of work to figure out how do we build models that have triadic closure that don't lead to this runaway triangle formation. So that type of phase transition is well known, but this one wasn't. The reason to understand why this is surprising, it's helpful to come back and look at the model in a little more detail. So as I said, this is a very simple 2-parameter model family that represents the core of what would be a more elaborate model. And so it has 2 things in it. It has the edge count, and that's just governing the propensity to form ties. And it has the count of concurrent vertices, that is vertices with 2 or more ties. And this normally has a negative parameter on it, right? So this expresses a norm against having multiple partners at once, which is common in many settings that we study for sexual contact networks. And so why is this a surprising thing that we see a phase transition? Well, the surprise is that we can prove using something called a Bernoulli bounds analysis that the tie probability in that model is bounded above and below by numbers that don't scale with n, and in fact are very well behaved. So we can actually put the upper and lower bounds on the chance of a tie between 2 people, and it never runs away and it never becomes very big. So you don't get like a density explosion. In fact, you can't. So it was thought that such models could not have phase transitions. And yet here we go, we found one. And so it's surprising that such a simple, innocent little term could lead to this sudden disconnect where you suddenly go from this dense regime, relatively speaking, where there are multiple ties to the sparse regime where you have very few and back. And so the question is, how can we understand what's going on in that phase transition? So to understand that, we first need to figure out what is the phase structure of the network. And so if we study this, it turns out that it sort of schematically works like so. So we can divide our network kind of into 2 regimes or 2 phases. One indicated by the part here labeled with B. And this is the part of the network where people are concurrent, so they have multiple partners. And then there's a regime marked by C where we have no concurrent partners. And so we can think about dividing a mixed network into 2 parts, the parts that are concurrent and the parts that are not. But what Pavel ran into is that, if you create the parameters of the model, you can create a situation where the network starts out being very, very sparse. So almost everyone is in that sparse phase. And then very suddenly, without warning, everybody can swap into the dense phase, the concurrent phase. And the question is, how do you get this radical transition from one to the other? So what's happening as we go from one part to another? So to understand that, we're going to borrow some techniques that have been used to study phase transitions in the StatMech context. And in particular, right, we need a way of charting a path from one extreme to the other. And to do that, we're going to introduce something called an order parameter. So what's an order parameter? An order parameter is a function of the graph. It's a numerical function, and it's defined to be 0 when we're in one phase. So here it's going to be 0 in the dense phase. And again, I emphasize the dense phase isn't that dense necessarily, but it just means people have more than one tie. And it's going to define to be 1 when we're in the sparse phase. So it's going to go from 0 to 1 as we move from one phase to the other. And in between, it's going to take intermediate values. And so we're going to choose the order parameter here to be 1 minus the fraction of nodes that have concurrent ties. Or if you like, it's the fraction of nodes that are non-concurrent, or that are isolates, or that are pendants, that are monogamous, right? So if we think of this as a social norm, this is going to be the fraction of nodes that satisfy the social norm. And that can be all the way from 0 when we're in the dense regime to 1 when we're in the sparse regime. And this gives us a tool for measuring where we are in the phase transition as we go from one place to another. So that's one tool we're going to borrow. And another tool that we're going to borrow is the idea of temperature. Now, what does temperature mean for a social network? Well, as Robbins and colleagues showed in a paper some years ago, and this has also been work done by a lot of other people, including Peyton Young and other settings dealing with stochastic choice model. There's this duality between models like ergoms and the physical world, where if you think about the equivalent of changing the temperature in a physical setting, that's like taking the ergom parameters and scaling them. And so in particular, if we lower the temperature, that's like making our parameters more extreme. It's like making our social forces more and more effective. And if we think about raising the temperature, that's like weakening those social forces. It's like drawing the parameters back to 0. And indeed, there's some nice dualities under some conditions. One can even show if where there's a game theoretic underpinning that if you cool the network all the way to temperature 0, this makes it act like the actor is irrational. And in fact, the modes that you get are Nash equilibria. So there's some very beautiful kind of game theoretic ideas under there. But for us, the thing that's useful about it is this gives us an easy way to think about studying the system, and that we can vary the parameters systematically by scaling them up or scaling them down. And then we can look at how system behavior changes as we modify those parameters. It also gives us some convenient points of reference. So for instance, it turns out that there is a particular temperature that is a scaling of the parameters called the critical temperature, such that above the critical temperature, the two phases can't coexist. You can't get both of them as locally stable solutions of the graph. And so that means that gives us a way to find a place to scale the parameters so that if we study the behavior of the parameters around that, it will give us, allow us to see what's going on in the phase transition. So it helps us identify where we should be putting the parameters to see some action. Another thing that we can do is we can look at the stability of these different solutions. And to do that, it's useful to work with a quantity called the free energy. And so in a social setting, what does a free energy mean? It essentially is a quantity that scales with the negative log state probability. So it's like the log likelihood. So it's like proportional to that, the negative log likelihood. If you like, you can just think about it as when the energy is low, the probability is high. So the system likes to minimize the free energy. The nice thing about working the free energy is that we can calculate it numerically without having to use MCMC, at least in this case, because we have an approximation to the partition function. That's a long story that I'll spare you with. But we don't have to use simulation because simulation is very costly and difficult across the phase transition. Now, we also can use that, and in fact, I will show you some examples where we use simulation as well to also round out our picture. So given these tools, what can we now say about this phase transition? Okay, so to start with, what I'm going to do is I'm going to look at these two extreme phases, and I want to see kind of how does the stability change as we change the parameters. And so here, this plot on the left gives a sort of schematic way of looking at that. So here on the x-axis, what I have is the order parameter. And so as a reminder, I've got those little graphs to show you when the order parameter is 0, we're completely in that dense world. As the order parameter moves to 1, we are moving through the space of graphs to the, or space of distributions of graphs really to the sparse phase. And then on the y-axis, we're going to scale our parameters. So this is the scale relative to the critical temperature. So of course, above that, that's the point where the phases can't coexist, above 1. And then I have found the energy minima. So that is, those are modes in the probability distribution on the order parameter. And every one of those I've indicated with a dot here. So numerically, we can find all the places on the order parameter that are local modes in the probability distribution, so they're locally stable. And then we can assess, is that a local mode carrying a lot of probability mass or very little? So if it's carrying very little, that would imply, well, if we started there, we might stay there for a while, but we're not likely to go there from the start point, and we're not likely to stay there for long. On the other hand, if it has most of the probability mass, right, then that mode is likely to be favorable. So if it's blue in this picture, that means it carries most of the probability mass and it's stable. Otherwise, if it's red, it's not. And we see this very characteristic pattern where there's a large range of parameter values where both modes are locally stable, but they're not globally stable. And so in particular, as we raise the temperature, we can see that the dense phase becomes more stable. If we lower the temperature, eventually that stays destabilizes, and now we transition to the sparse phase. And so indeed, we can see that there's a dramatic shift where all of a sudden we go very abruptly from one extreme to the other. And indeed, if we look at this transition, it has this characteristic behavior. It's something called hysteresis, where if we imagine if we started the network, say, in the sparse phase and then raised the temperature, we would tend to stay there for a while, but then eventually we would suddenly transition across to the other phase. And then if we lowered the temperature, it would eventually transition back, but there would be kind of a gap in between. It wouldn't immediately start. There would be a lag if we went from one to the other. And that is characteristic of what's called a first order phase transition. So these phases can coexist, and there's this hysteresis structure. Now, if we think about what the average order parameter would be like across this, we can verify that by simulation. So the plot on the right shows sort of almost the same thing, but sideways. So here what I'm doing is I'm varying the temperature and then simulating graphs and saying what's the average of where I am on that transition. And indeed, we see just what we would expect, where if we start, say, in the sparse phase, we increase the parameter, we get an abrupt transition where very suddenly we go from being very much in the sparse regime to very much in the dense regime. So there's just not much between these two extremes. exactly as we would expect for this phase transition. So to understand then what's governing the phase transition, we might now ask, well, okay, how is it that this occurs? Is it that something is going on that changes the behavior of the dense phase, or is it something going on about the sparse phase that's doing it? And to see that, it can be helpful to look at what the free energy is doing around that point where the stability transition occurs. And so here what I've done is I've taken the order parameter and I've plotted the free energy. That's again related to the negative log probability. So if you like, lower values, right, are more favorable. I've plotted it across that order parameter. And so we can see that there are, again, two big minima here, right? The minimum associated with the sparse phase and the minimum associated with the dense phase. But the stability of that is going to change as I change the temperature, right? So if I cool the system down, then the plot on the right is lower, it's more stable. If I heat it up, it tilts the other way, the one on the left is more stable. That makes sense. But what we can see is that that change is not governed by what's going on in the ordered phase or the sparse phase. That stays almost exactly the same. The change is governed by what's going on in the dense phase. That's actually the energy change that's driving the system. And so then the question is, what is that driven by? There could be two factors here. It could be due to the strength of that social sanction, the strength of that concurrency penalty that's saying you shouldn't have multiple partners, or it could be due to the entropy of this process as I change things. And it turns out it's governed primarily by the entropy. So here's on the left, this is just our free energy picture again. Now I'm just showing a wider range of temperature. So it shows just what we saw in the plot, the previous plot over a larger temperature range. Again, it's the free energy change of the dense phase that governs what's going on. But if we now separate out the part of the free energy is just due to the entropy, we can see that the entropy is really what's driving the gap. And the entropy change is, of course, occurring in the dense phase, not the sparse phase. So this is actually something that has to do with how many ways there are to make the graphs. Now, how would that be the case? How do we interpret what's going on? Well, there are two ways to think about what's going on. There's kind of a macro view and a micro view. So I'll start with the macro view. So as we change those parameters, right, one of the things that we're changing is we're changing the overall mean degree, right? In general, ties are kind of disfavored because we don't have that many partners. And there's this concurrency penalty. When we heat the network up, on average, the mean degree is higher. And that means that that concurrency penalty to try to force us into the sparse phase has to do more and more work kind of sanctioning or censoring ties, right? So this is just not very likely to happen, right? The chance that I'm going to successfully quash all of the ties in my social norm is not very high. And so indeed, we tend not to be in that sparse phase. On the other hand, as the temperature goes down, the baseline mean degree is already small. So there are about as many ways to make networks that don't have that restriction of concurrency as ones that do. And we don't have to censor very many ties in order to get there, right? So it becomes easier to get there. So there's sort of a logic here, which is in essence, it's easier to defend a norm when there are not many opportunities to violate it. So in that part of the regime, in that part of the system regime, the norm does not have a lot of opportunities for violation, and thus we are able to stay in that phase much more easily. There's also a micro way of looking at this. So from the standpoint of a given individual, that model actually implies that there is a cost to having multiple partners. So if I've got one partner, getting another one is taboo. But once I've crossed the Rubicon and I've got multiple partners, there's no additional sanction for having more. I might as well have yet more partners. So if I'm in a world where I would have a bunch of partners except for that sanction, if not for that sanction, then once I've transgressed, right, I'm likely to wind up acquiring more and more partners. And once I have a bunch of partners, even though I'm incentivized to reform myself, I'm not likely to get into a situation where I can get down to few enough partners where just losing one more partner is actually going to get me right with the concurrency term, right? So once I've embraced the concurrent lifestyle, it's very hard to go back. So this is like one of these, kind of stereotypical parental scare story models, right? Where you have some kind of cult, and once you're drawn into the cult and you form all these ties with other people in the cult, now you're consumed and you can't get back. You played D&D one time and now you're sacrificing people, and it's a terrible thing. And there's no way out of this lifestyle, okay? And so in a sense, this model kind of has this thing, sort of parental scare story kind of built into it. Another way to look at it is that from the temperature change standpoint, right, as we said before, when the temperature is high, this would imply that if it weren't for that sanction, I'd probably have a lot more ties. And so trying to sanction me is trying to keep me from doing something I'd be doing a lot of. And it's harder to get people to do that versus something that I wouldn't do anyway, right? So it's easier to obey the rule when I don't have that many opportunities, right? So when the temperature is low, I wouldn't have that much going on anyway. So I don't have to censor many ties, right? So that, again, from a norm standpoint, we kind of think about it. If I have a norm, it tells people to not do things they would do all the time, like stop eating. Okay, people aren't going to obey that. But if we have a norm to tell people to stop doing things they don't have opportunities to do, like don't stop eating elephant shrews, okay, that you can live with. Okay, it's a lot easier, right? And so in this case, it really matters that baseline makes a huge difference for what's going on. And so once we see it this way, we get a lot of insight. Another way we can use that order parameter to get interesting insights from in terms of potential microprocesses is to go back to our traditional simulation way of doing things. And we can simulate microdynamics, for instance, using a simple choice model. But we can still use the order parameter to organize those simulations. So one of the things we can do is we can run a whole bunch of simulations of networks going in and out of one phase to another. And then we can look at the edge formation dissolution events that occur. And then at for different kinds of graphs, and then look at the rates of those events as a function of the order parameter. And so in this model, it's very simple to do that because they're really only, the only thing that govern those event rates are going to be whether the individuals involved are isolates, pendants, or concurrent vertices. And so if we run simulations and we actually tabulate the rates, we get something that looks like this. And this is again from Metropolis Dynamics. So here we're going to start out the other direction. We're going to start out in the ordered phase and then move over to the disordered phase. And here I've plotted on the y-axis the event frequencies. Here I'm only showing formation events because it turns out dissolution events are not very interesting in this case. I have them on log scale, right? So the changes are quite dramatic. We can see that at the beginning, as we would expect when we first start forming ties, they basically have to form among isolates because there are not many more things to do when we first start out. But once we get a few concurrent vertices, once a few have succumbed to the concurrent lifestyle, the thing that begins to now take over are events where concurrent vertices start to capture isolates. They start to absorb them. Those, once they've been now captured, if they form even one more tie, they become concurrents. They start vacuuming isolates up, and this again becomes a very common event. Then the next thing that starts to happen is you begin to get extensive tie formation among the concurrents. So once you've gone concurrent, you might as well form more ties. You're not going to gain anything in terms of the social sanction, so you might as well do it. And so what that does now is that takes those concurrent vertices and it pulls them from any hope of redemption. Right now they're lost to that sparse phase, and meanwhile they continue to seduce more isolates and pull them in. And so bit by bit, the concurrent phase drains the isolate phase out of the network until finally everyone is in the concurrent phase. Interestingly, by the way, if we look at pendants, we see that pendants don't get much activity here. So although they do exist and they're important transients, most of the edge formation events do not involve pendants. We don't see things driven by pendants merging with other pendants, for instance. That's very rare. So mostly what's going on involves interaction between concurrents and other concurrents, or concurrents and isolates. And the pendant interactions are actually very rare. And this is, again, something that we wouldn't otherwise necessarily know, but having this order parameter view makes it really easy for us to see what's going on and gives us a lot of insight in what's going on in the network. So now I'm low on time. So what I want to do just in the last couple of minutes is switch gears a little bit and talk about, having now used these kinds of ideas to give insights into social systems. I want to talk about how we can use social ideas to give insights into physical systems and how we've used some of these same network models to study things outside the social sciences. So in particular, I'm going to talk about some work I've been doing in a collaboration with Rachel Martin's group at UCI, studying the biology of protein fibrillization. So proteins, of course, are one of the biomolecules that make up living organisms. A big chunk of your body is made of proteins, and proteins serve many important functions. Unfortunately, proteins also do something else, which is that they aggregate. So proteins are prone to undergoing a phenomenon where they hook onto other proteins and form these very long, very, very sturdy structures called fibrils. In particular, they're prone to forming what are called amyloid fibrils. Amyloid fibrils are characterized by a very particular, something called a cross beta sheet structure. They're very resistant to degradation. And the bad thing about that means that they can build up in your body, in your organs, in your tissues, inside your cells in some cases, sometimes outside your cells, and they cause a lot of havoc. And this is in fact a driving mechanism behind many diseases, most famously Alzheimer's disease and Lewy body dementia, but also type 2 diabetes and a number of other diseases as well. So understanding this is a really important problem, especially in an aging population. It turns out that this is very generic. Almost all proteins will undergo fibrillization under some conditions. So it is quite common, but it is very hard to study. And one reason is because it takes a long time to happen. And so conventional modeling techniques that are used to study this, that actually track each atom, just simply cannot work at the scale. And so there's a huge demand for simplified models that can reproduce the basic structure of fibrils without having to do all that complex stuff. And since we build models that involve the emergence of structure from simple interacting parts, we got interested in the question of whether we could use the models that were originally produced for social networks to actually study fibrillization as well. So just to give you a flavor, this is what fibrils are kind of like if you look at them under electron microscope. So you can see different kinds of fibrils. They all have this kind of characteristic structure. Here there's also sort of an atomic model to give you a sense of what they're like if you were to zoom in on them. And although there are many, many kinds of fibrils, it turns out that they all have this kind of repeating form. And so in order to figure out how to model these from a network standpoint, what we did is we said, well, let's start with a simple-minded approach where we're going to think about every individual protein as a node, and two proteins are going to be tied to each other network if they're hooked to each other non-covalently. And so then we went to this thing called the protein data bank, which has the structures of all, among other things, all the amyloid fibrils that have been solved to date. And we used some energy approximation methods to figure out what are all the ties between the monomers in those structures. And we categorized them all based on the kind of network topology we found. And so what we discovered is that all the things that have been solved to date fall into just 5 categories that you see here. And some of them are somewhat complex, like this 3 prism you see on the right. Others, though, are very simple, just sort of stacks, like this one ribbon on the left. And so although we can envision other kinds of topologies, all of the things that we've seen in practice form into this one of these very simple categories. And then the question is, could we have a network model that could reproduce that? And so it's natural to think about, having just pointed out, well, gee, you know, we have these ergams and we know how to model emergent structure with ergams. And we've just seen that ergams have a statistical mechanical interpretation as well as a social one. So what if we think about using an ergam to actually model this kind of process? And indeed, we can do that. And it turns out that we can, using a very simple ergam form with the same kinds of terms we might use to model social networks, we can actually recapitulate all those fibril topologies. And for want of time, I'm not going to go into depth about it, but I just point out that all these terms that we use normally for social networks can also be used here. They have different meanings. So we do, of course, have to think about what they mean in that setting. You can't just blindly grab a model and stick it from one thing to another. So there's a lot of details that are involved in that. But the bottom line is, indeed, we can do that, and then we can simulate draws from that model and indeed show that we can recapitulate the structures. So in fact, we get these in equilibrium. We get these forms that are exactly the kind of things that we see in nature. And in fact, we can even recover things like defects in the fibrils and the formation of small oligomers, which are often thought to be the toxic species in some disease processes that also naturally emerge without our having to force it from that simple model. So those simple mechanisms, we're familiar as social scientists with how these simple mechanisms can lead to emergent structure. Well, the same thing happens here as well. Another cool thing we can do is that we can generalize that ergam by adding dynamics to it and using techniques that are very similar to those pioneered by Johan Koskinen and Tom Schneiders and others in the context of social networks. We can actually look at the network dynamics. And this lets us see some really cool things about how these things form. And so I will close it out by showing you a movie of this, just because it's really interesting to see how some of these models that we think about in a social world can generate quite dramatic structure. So here what you're seeing is a movie of fibroformation by one of these network models. So every vertex here is a protein, and there's a tie between 2 proteins if they're bound together non-covalently. And so if you start out with a solution of free monomers and you let them go, the first thing they begin to do is they start to aggregate, right? So they start to stick together. And the aggregates they form at first are very random looking and unstructured. And indeed, they form what might be known technically as a blob. Or if you're being really picky, you'd call it a gel, right? So it's a very unstructured thing. And if you look at this, you might think, okay, well, we're done. There's no fibril, it's boring. But we're going to let it run anyway. And if you notice, if you look at the blob very carefully, you'll see we've got some vertices that are marked here in yellow. So those are vertices that are in locally fibrillar conformations. Even though you can't really see it, locally they're in something that looks like a two ribbon. And if we keep watching our blob because we're bored and we don't know what else to do, we'll notice that, gee, we see more and more of these yellow vertices. And in fact, the yellow vertices are starting to recruit their neighbors and making more of their neighbors locally fibrillar. And in fact, if we keep watching this blob, we can see that something funny is going on. And that is that the blob is starting more and more to organize itself. We see more and more fibrillar structure emerging and more kind of structure in that initially random blob. And if we keep watching it, something really amazing takes place. And that is that that big, ugly, random looking blob organizes itself into a very, very rigid, organized two-ribbon fibril structure. And indeed, we see something that looks just like we would expect with nature, coming out of nothing more than the emergence of these simple forces. And that whole model is driven by just an ergom of the same kind we might use for social networks. The parameters are different. It only has 4 parameters in it, though. Four parameters, 4 terms in the model. And so this is ultimately an example of something where we used modeling ideas that were originally created to study things like friendship and sexual contact networks and advice-seeking relations. And we're able to attack a problem that was very, very hard to model from a molecular standpoint. And this is the first class of models that actually has been able to recapitulate that entire process from start to end and reproduce those topologies. And we can do it on a laptop. And so by using tricks that come out of social sciences, we've had to think hard about how to take complex systems and look at emergent structure, we're able to attack these other problems as well. So really, this borrowing is a two-way street, right? We can learn things about other systems by using social ideas, and we can learn things about social ideas by using physical ones. So in the interest of time, I'm going to wrap it up there. Hopefully, I have convinced you that statistical network models have a lot of avenues, not just for fitting data, but also for theory. So of course, having models that work is a sine qua non. We have to be able to do that, but then we want to understand them. And sometimes, in fact, it can turn out that little patches or fixes that we stuck in the model just to make it work that we didn't understand at first actually turn out to have really interesting insights, as we saw with the Kravitsky reference, that can give us clues about what kinds of microprocesses are going on. Another thing that what I talked about today emphasizes is that when we go and we look at network structures that we see, many aspects of them are arising from unobserved dynamic processes, including things that occur very, very quickly relative to the tie formation process. The details of these things are blurred out due to timescale separation. We don't see them, but they're still there and they can leave their fingerprint on the network. And so having a macroscopic network model can still give us insight into what those microprocesses might be. And vice versa. If we have a microprocess, being able to derive the macro conclusion is, of course, valuable as well, right? And this is, of course, a common theme in analytical sociology. One nice thing about the ergom framework is that being kind of by nature sort of statistical mechanical, it gives us a lot of formal tools that make it easier to do that kind of mapping in a formal way. I think likewise, it's useful to recognize when you invent a model, it does one thing and it has a formal representation that's equivalent to something else. Figuring out how you can use tools from that other formulation with your original one can be really helpful. So here we've shown how we can use insights based on the links between ergoms and StatMech. This has allowed us to look at social systems from a new angle, revealing hidden assumptions on our models and suggesting new ways of answering our existing questions. And it's also allowed us to take models that we produced for social purposes and then use them to answer other questions, including ones that are critical for human health. So to end, I want to recognize my group and also my collaborators on the fibro work, particularly Rachel Martin and her student Mekan Helkar. And in my group on the fibro work, my now former postdoc, John Mark Grazioli, and UAU, former PhD student, did a lot of important work on that. And I want to thank all of you for your time and attention, and I'm happy to take questions in the remainder of time we have.
Thank you very much, Carter, for this very, very interesting talk.